Folks, how we doing? So what we're going to talk about today is our last little section on vectors. We're going to look today specifically at forces. So we just spent some time looking at two-dimensional motion, both launching things horizontally, launching things at an angle. So today we're going to focus more so on the force aspect of it. So we're going to look at two-dimensional forces. So again, a force is just any sort of push or a pull that's acting on an object. But specifically, we're going to look at two-dimensional forces. So those pushes or pulls are now going to act in two directions at the same time. So take, for example, the force here acting on the dog. Let's say I'm pulling back on the dog's leash. This case, I'm pulling at an angle. So just like we talked about with vectors, that while I'm pulling at an angle, that I'm pulling both, in this case, backwards to the right, and I'm also pulling the dog up at the same time. So this rightward, or this angled force, has two components, both in the upward direction and in the rightward direction. Again, this is different than what we've looked at before with forces, because specifically with forces, we only looked at forces acting in individual directions. So we talked about, for example, like gravity acting downward, a normal force acting upward. We talked about like applied forces and friction, but now what we're going to have is, could be possibly an applied force, wherever it is, but instead of looking at something acting in one direction, now we're going to have a force acting at an angle, which is going to change the problem slightly. So the very first thing, kind of just like motion, is to understand forces acting at an angle, we got to understand the whole component aspect of it. So let's say that I have ambitious little Fido that's pulling back on his leash, and let's say that I pull back on that leash with 60 newtons of force at an angle of 40 degrees above the horizontal. So again, above the horizontal means that if I were to say draw a line going straight to the right, 40 degrees, kind of think of that as northeast. So I want to know what is the component of that force. So again, component's going to describe how much of that force is acting in each direction. So here I would have a force going to the right, and I would also have a force going upward. Those are the two components. So when I think about this, what I'm going to look at again is thinking about a right triangle, that I would have these two components, one right and one up, that as a triangle would form that overall force of 60 newtons. So our goal is to find these two components by using, again, sine and cosine. So to find the horizontal component, I would use the cosine of 40 times 60. Again, that's going to give me a percent times 60. And then to find the vertical component, I use the sine of 40 times 60. So I'm going to use that same angle, but again, look at those two different trig ratios to get the values. So what that would give you then is 46 newtons in the horizontal direction, and would give you about 39 newtons in the vertical direction. So again, that's 36. Again, that's describing the component of that force in each individual direction. All right, so once you try this one, I have a 400 Newton force being exerted at a 60-degree angle to move the railroad car eastward along the track. So what I'd like for you to do here is try this one on your own. I have the 400 Newton force acting at that angle of 60 degrees. Think of it as below the east, so kind of below the horizontal. And I want to know what are the components of that force. Go ahead, pause this one, try this one on your own. All right, so using sine and cosine again, you should get the two components. So for the horizontal component, using cosine, you'd get 200 newtons, and using the sine to find the vertical component, you get 346 newtons. So again, very similar to what we did with motion, but now we're talking about how much push or pull is in each individual direction. All right, so as we talk about forces, again, when we looked at Newton's laws, we talked specifically about the whole idea of balanced versus unbalanced forces. And that was really the thing that drove our entire unit on Newton's laws of motion. Again, talking about if forces are balanced, that means everything up and down, left and right, everything is going to be equal and opposite. And that's going to cause an object to move at a constant speed or stay at rest. And then things are unbalanced, that means we're going to have more force, either up, down, right, or left. And that's going to cause an object to accelerate, which means to speed up or slow down. So the very first thing is we're going to apply this idea of two-dimensional forces to the things that we already know. So applying Newton's first law when things are balanced, there's a branch of physics called statics, which is going to focus on when objects are in a state of what's called equilibrium. Equilibrium just means a state of balance, where everything is going to be equal and opposite. So take, for example, these two diagrams. This would be a case of equilibrium because I have all my forces, 50 up, 50 down, 30 right, 30 left, they're all balanced. Same thing here, 50 up, 50 down, 75 right, 75 left, again, they're all balanced. So that would be in a case of equilibrium. Specifically, the branch of physics that deals with what's called statics is analyzing the forces acting on stationary objects. Statics just simply means stationary, okay, where everything is balanced again. So Take, for example, here I have a little mass that's hanging between two scales. So here I have two ropes. This little mass is hanging there, you can see by the hook. These scales are reading the forces on each one. But the idea here is that if this is in equilibrium, this force, obviously this mass is hanging down, so gravity's pulling down on it. But since I have a rope here, you'll notice that there's essentially two strings that are pulling on this object. So to think about what we're going to do with two-dimensional forces, how this applies to equilibrium, is that this object is in a state of balance. All the forces, again, since it's not moving, are going to balance out to equal zero. But what we have is that we have a force acting downward, I have a force acting up and to the right, and I have a force acting up and to the left. So essentially I have these three forces. Okay, and what equilibrium means is that everything's going to be balanced. So to understand this, we're going to think about components. B, for example, is going to have a component going to the right and going upward. I'll draw those in red. A is going to have components going to the left and upward. So when you look at this in terms of up, down, left, and right, when we look at the individual directions, you'll notice that each of these two components, each of these two vectors have a component upward, and each of these vectors have components right and left. So in terms of balance, notice I still have a right and a left. I still have an up and a down, but the only difference here is that when I look at like the ups, for example, I have two up arrows compared to one down, and then I have a right and a left. Now my picture's not really drawn to scale, and again, the forces for A and B are going to vary based on this. But the idea is that with statics, when we look at the components, we can still see the idea of a balanced forces by just knowing the thing's stationary, but what we're going to have to do now is start to consider the components of those forces. So let's take, for example, a situation in which we have something that is balanced forces. So I have here, say in example A, I have a picture of this beautiful lady that's just hanging from two strings, and you'll see that the strings form 45-degree angles, and notice the forces in both strings are 30 newtons apiece, and being as strings are tension forces. So my goal is to determine the weight of the picture. So to understand this, I'm just going to draw a little force diagram to the side. So I would have obviously the two tension forces acting in their respective directions, and I know that the forces are 30 newtons apiece, and I know that those forces are acting at an angle of 45 degrees each. Okay? But I also know that the picture has its own weight, so I'm going to consider now that the force of gravity, which again is equal to the weight, is pulling that thing down. So my goal, given this situation, is to determine the force of gravity. What does that need to equal? So the force of gravity is obviously a downward force. So any sort of downward force needs to be balanced by upward forces. This obviously, when you hang a picture from a wall, this picture is not moving. So this would be a case of equilibrium or statics, where everything's stationary. So how does this downward force get balanced out by these two forces that act at an angle? It is because each of these forces has components. There is a component of each of these forces acting in the x direction. One goes up and to the right, one goes up and to the left. So notice there's a right compared to a left. One goes up and the other goes up. So here's the idea. Each of these little tensions, each of these strings, applies an upward component. And what I got to think about is this, is that I have two upward components and I have gravity that's pulling downward. So essentially what has to happen if I want to find the force of gravity, whatever these two components are, if I take those two components and add them together, that should equal the weight of that object pulling down. So essentially all I have to do is figure out what are these two components. To do so, to find the vertical components, I need to use sine or cosine. So in this case, given the angle of 45 degrees, I'm going to have to use sine to find that upward component. And I'm going to have to do this to find the upward component for both. Now recognize that given that both forces are the same and the angles are the same, both upward components are going to be the same. So if I just simply do the sine of 45 degrees times that 30 newtons of force, that should tell me how much upward force I have for that component, which is about 20, I'll just say 21 newtons, I'll round to. Okay? So that means if this force is 21 newtons and that one's also 21 newtons, that since those are both going up, the weight of that picture needs to be a total of around 42 newtons in order to balance those things out. So what we're using here are the component of forces and the idea of equilibrium to try and solve for unknowns. So looking at example B, similar idea. All right, we have a sign that's being supported by a cable, and you're given the angle of the cable about 30 degrees off of that horizontal bar. You're given that the mass of the sign that's supporting is 50 kilograms, and our goal is to determine the tension in the cable, okay? So if we look at the forces acting on this point here in the middle, what we have is we have the force of gravity pulling downward. That's the weight of the sign. We'll have the tension pulling up and to the left, and then the horizontal bar, this one's a little tricky, but the horizontal bar is actually pushing to the right on this point, okay? So we can call that, let's say, an applied force. We have the weight of the object and then tension. Our goal in this case now is to solve for the tension. So obviously the tension, as we look at the components, is acting both to the left and is acting upward, okay? So my goal is to solve for the tension. Now, what I know right away is that I know that the mass of this object is 50 kilograms. So what we talk about is if we know the mass, we automatically know the force. So I know that the force of gravity. I know that the object's weight, or the force of gravity, is 500 newtons. Now, based on things that we've talked about before, that gravity is pulling downward. So if this thing is not moving, if it's balanced, that means this upward force of tension, okay, the component of tension, I should say, is also 500 newtons. So what we have is this, and I'm going to draw this below. We are trying to figure out the value of tension. Tension has two components. It has a leftward component, which I don't know, and it has an upward component. And what we just figured out is that the upward component of tension is 500 newtons. Also, in the angle between these two things is 30 degrees. So I can use, again, the trig functions to solve for tension, but here's the only difference, is that now I know one of the components, and my goal is to solve for the resultant vector. All right, so again, based on this angle, this vertical component is going to be the opposite side, so I'm going to have to use sine. But when I use sine, sine of 30 degrees equals the opposite side, which is 500 over t. So now the thing that I'm solving for is going to be the denominator. So I'm trying to figure out what is that resultant vector based on the component, okay? Sine of 30 is going to give me a half. So I essentially want to know 500 divided by what would give me a half. So obviously by thinking about what the tension would be, in order to get a half, I know that my tension needs to be 1,000 newtons. Oops, that's only 100 newtons. So what we did here is we kind of did the same way. We still considered the components, but now in this case, just how we solved it was differently. By knowing the weight, we knew one of the components, so then our goal is to solve for that resulting force, that tension, based off of one of the components in the angle. But again, this is showing that relationship between equilibrium, where everything is going to be balanced.